Operation Teapot, the latest addition to our Encyclopedia of Nuclear Testing, bears the dateline Spring 1955. For the fifth time in continental testing, the symbol of nuclear power rose over the mountains of Nevada. This series encompassed so many objectives that preparations began while there was still snow on the mountains surrounding the Nevada test site and in the valley north of Yucca Flat. In contrast, the series came to an end in May amid the bloom of desert flowers. 14 times during that period, the blinking blue light on the pole above Camp Mercury indicated the shot was on for the following day. Although the 7 programs conducted by the Military Effects Group included some 50 different projects and participated in all 14 shots, the most important military effects studies were concerned primarily with 3 shots: an underground, a tower, and a high-altitude burst. The S, or underground shot, was scheduled to extend our knowledge of the cratering efficiency of nuclear weapons. In 1951, the first underground nuclear shot was fired during the Jangle series. Yield 1.2 kilotons. Depth of charge 17 feet. The apparent crater had a radius of 130 feet and a depth of 53 feet. The true crater was never measured. Therefore, on Teapot, a new technique was planned to determine the depth and diameter of the true crater. To permit correlation with the Jangle U results, a device with the same yield, 1.2 kilotons, was chosen, and the shot point was located near the old Jangle U crater, but at a sufficient distance to ensure against any interaction. Vertical holes 8 inches in diameter were drilled into the ground in a straight line bisecting ground zero. Sand mixed with a colored dye was poured into each hole, red, yellow, and black respectively. 3 holes, including the one at ground zero, were at a depth of 200 feet. Additional holes were dug, varying in depth from 150 to 50 feet, for a total of 21 holes, the outermost being 350 feet from ground zero. After the burst, when the soil has cooled radioactively in 6 to 8 months, the remains of these colored columns will be excavated, the dimensions of the true crater established, and the zone of rupture defined. At ground zero, or rather under ground zero, a weapon hole 11 feet in diameter was dug to a depth of 70 feet to permit a charge depth of 67 feet. It was expected that this depth might produce a change in the TNT cratering equivalence of the nuclear charge, with consequent revision of the scaling curves for underground shots as extrapolated from the Jangle results. In addition, it was hoped that further data could be established on the relationship between atomic detonations and high explosive tests in Nevada soil. With such a relationship confirmed, HE tests could be made in other soils at various depths to be representative of the target applications throughout the world. The actual digging of the hole and the placement of the weapon also served as a stockpile to target sequence test of ADM, or atomic demolition munitions. ADM would have great use in barrier systems or retardation operations to destroy airfields, dams, bridges, tunnels, mines, underground structures, or to create large craters as obstacles. And as a basis for training, studies were made of the problems encountered in planting such king-sized land mines. Estimates of the time required to hole out such a device were substantially confirmed. Secondary objectives of the underground shot were to obtain additional data on fallout and residual radiation, base surge, ground shock and air blast, and earth shock loading. Studies of radiation on this shot were especially significant because of the immense amounts of soil that would be contaminated and dispersed over the surrounding terrain, both from the base surge and fallout. Collectors and samplers, badges and dosimeters were set out before the burst at locations predetermined by the wind forecast. Those in hot areas were set out on trailers attached to long lengths of cable so they could be hauled out safely. The objective was to determine the distribution and intensity of fallout and to plot isodose rate contours on the radiation field as a factor of time. Transient surface and underground phenomena measurements included air blast, earth pressure, acceleration, and strain, all as functions of time over a range of 200 to 600 feet from ground zero. A number of flexible measuring devices were installed at a depth of 15 feet at a ground range of 300 feet to determine basic earth loading data for more efficient design of underground structures. Also, studies were made with modified dugway boxes to correlate the results with previous findings from small HE charges and the Jangle underground shot. After arming and insertion, the backfill of the main emplacement shaft and the access shaft was exceedingly well tamped to eliminate any surrounding air spaces. H hour was 1230 hours on 23 March. As expected, the base surge phenomenon was clearly visible. The throwout reached a height of 700 feet and a maximum diameter of 1,300 yards. The diameter of the base surge extended beyond 1,760 yards and definitely carried radioactivity of high intensity in the upwind and crosswind directions. Time of arrival data, downwind from ground zero, show that the fallout traveled at about 2 miles per hour ground speed. Cloud growth studies indicated a maximum height of 10,500 feet at 10 minutes after detonation. Radiation surveys were made by lowering an instrument from a helicopter over the crater at H plus 1 hour and 40 minutes. Calculations indicated that the dose rate had been 6,000 Roentgens per hour at H plus 1 hour, just inside the crater lip and extending out to 150 feet on all sides of the crater. 90% of the activity on the crater lip was in the first 12 inches of depth. In general, good correlation was noted between the gamma field intensities as predicted from HE and nuclear data and the observed intensities. Using the T to the minus 1.2 decay factor, a plot of distribution and intensity of fallout at H plus 1 hour showed almost 1/10 of a square mile enclosed by the 3,000 Roentgens per hour line, almost half a square mile at 500 Roentgens per hour, and about 1 1/4 square miles at 100 Roentgens per hour. The 20 Roentgens per hour area reached about 4 miles downwind. Samples of the soil in the fallout area, analyzed by a scintillation spectrometer, revealed that the residual gamma spectra were predominantly those of fission products with small amounts of neutron-induced activities in manganese 56 and sodium 24. Since ground personnel might be required to pass through or occupy an area in which there is fallout, a study was made of the nature of the radiation hazard. Human phantoms were set out in radioactive areas. Some in prone positions, some in standing positions, and some in areas that had been brushed superficially to determine the value of such a simple precaution. Results indicate that the surface dose from soft gamma or beta radiation in many cases was 20 times the average internal dose for a man lying prone, but that brushing the ground reduced this factor by 50%. Data from instrumentation on earth shock revealed that while inputs were lower than expected, nevertheless satisfactory measurements were obtained on transient surface and underground phenomena. Aerial mapping techniques were used to measure the apparent crater for comparison at a later date with dimensions of the true crater. From aerial stereographs, the depth of the apparent crater was computed at 90 feet, the maximum lip height at 19 feet, and the radius at 146 feet. The radius was less than expected. These results indicate that the charge depth does not appreciably increase crater radius, although the volume of material displaced is greater. An analysis of the data from the Jangle and the Teapot underground shots of identical yield leads to the conclusion that there is no significant change in cratering TNT efficiency over the range of charge depths from 17 to 67 feet for a yield of 1.2 kilotons. South of the underground testing area is Yucca Flat, location of Hornet, a 300-foot tower shot. Although Hornet was a development shot, a military effects study was made to evaluate the attenuating factor of a ground smoke screen against thermal radiation. As expected, it was found that a 75 to 90% attenuation resulted in areas where the fog oil smoke was heaviest. Out on Frenchman Flat, however, the Teapot schedule called for the most extensive military effects test of the series, coded as the Met shot. A tower shot of 28 kilotons expected yield, 400 feet above the dry lake, Met involved the greatest number of projects in two important objectives. First, destructive loads on aircraft in flight, wherein 3 drone jet aircraft were timed to be directly above ground zero at shock arrival time. And second, a study of the behavior of blast waves along different types of ground surfaces, particularly to obtain more information about precursor phenomena. Several low nuclear bursts on prior Nevada tests had revealed the existence of a precursor, or non-ideal blast wave, that preceded the main shock front. Shot 10 of Upshot Knothole formed such a wave, and drag-type targets were damaged much more heavily than by similar overpressures from Shot 9, which had an ideal waveform. For example, on Upshot Knothole, jeeps were exposed in both shots 9 and 10 to overpressures of approximately 9 psi. On shot 9, only moderate damage. On shot 10, a low burst, the damage was extremely severe, in many cases completely demolishing the vehicles at the same overpressure that produced moderate damage on shot 9, a high burst. Dynamic pressures were much higher for the low burst, which produced a dust-laden precursor blast wave. Was dust an important factor? Did the precursor increase the damage effectiveness of a low burst? Would a low precursor-forming burst be more effective than a surface burst? What effect did the characteristics of the ground surface have on the effects of a low burst? Answers to these questions were important objectives of the Met shot. The area layout of Met called for 3 types of surfaces: the desert, or dusty precursor-forming surface; the asphalt, or non-dusty precursor-forming surface, which would absorb thermal radiation; the water, or non-dusty, non-precursor-forming surface, which would reflect thermal radiation. North of the tower was the water blast line, a shallow artificial lake 800 feet wide and 3,000 feet long, which was flooded with several inches of water just before H-hour. Towards the south was the asphalt blast line, a smooth surface rolled flat upon the ground and also 800 by 3,000 feet in dimensions. To the west, the usual normally dusty desert surface of Frenchman Flat. Much of the instrumentation was duplicated along all 3 lines in order to correlate the results. Pitot tubes to measure the dynamic pressures. Pitch gauges to determine the vertical change in direction of particle motion versus time and distance. Snob gauges to measure the dynamic pressure of the air alone in the presence of dust. Density gauges to measure the density of air and dust, and to determine blast effects on objects of varying shapes. Spheres, cylinders, and force plates were set up at instrument stations. Throughout the Met test area, each instrument was ready to catch a specific clue that would aid in solving the problem of the precursor. What was the quantity and size of the dust particles carried by the shock wave? Dust samplers and beta densitometers would get the answers. Along the 3 blast lines, jeeps, as drag-type targets sensitive to dust loading, were parked at various orientations at predetermined distances from ground zero. Likewise, drag-type structural elements and simple shapes were positioned. Some were concrete cubicles with instrumentation mounted on them. Some were old Upshot Knothole structures, such as the bridge members and trusses, water tanks of welded and riveted construction, and several of the existing test structures. Some structures were covered with 3 feet of earth to evaluate such protection from a blast wave estimated at 17 psi overpressure and 120 psi dynamic pressure. A special study of the effects of positive phase duration was begun on this shot. 2 sets of buildings were erected of steel frames with 2 different types of wall paneling. Theory predicts that as positive phase duration is increased, the peak pressure required to cause a given level of damage is decreased for certain target types. In order to obtain positive phase durations differing by as much as 10 to 1, 2 shots are required for this study. One with a nominal yield in the kiloton range, and the second in the megaton range. For example, the Teapot buildings were to be exposed to a positive shock phase duration of less than 1 second at 3 to 7 psi, while later in the Pacific, it is planned that duplicates of these same buildings are to be exposed to a large yield positive phase duration of 5 to 8 seconds at lower overpressures. Since the water blast line afforded the possibility of a clear or ideal shock wave with classical free air characteristics, a study was set up to determine the structural response of fighter aircraft horizontal stabilizers. 6 F-80 and 3 F-86D stabilizers were mounted vertically at a high angle of attack to obtain lethal gust loading. Rounding out the blast program were miscellaneous projects concerned with military equipment, field-type fortifications, machine gun emplacements, dugouts, and trenches. Since the drone program required daylight for operating purposes, Met had the further distinction of being the first daytime tower shot ever fired at the Nevada test site. While the expected yield was 28 kilotons, radiochemical analysis indicated a yield closer to 22 kilotons. The results of the surface blast program on the Met shot turned out to be largely as expected. A pronounced precursor formed over the asphalt line due to the high absorption of thermal radiation. The strong precursor effects extended over a greater distance than over the desert blast line. In general, the greatest drag force was measured on the desert line where dust density was greatest. Dust loading of the blast wave apparently contributed to the high total force instrument readings. Actual existence of the high total force was qualitatively confirmed by jeep damage, which was much greater than on the asphalt line. On the water line, blast perturbations were observed within 2,500 feet of zero, and jeep damage in this area was greater than on the asphalt line. Essentially, ideal shock forms were observed over the water in the next 500 feet where the aircraft components were located. F-80 stabilizer damage was greater than expected, varying from complete destruction at the inner range to moderate damage at the outer range. However, the F-86D components received overpressures as high as 12 psi with no visible damage. Good data on high-level elastic loads were obtained. A project that aroused high interest on Met concerned nuclear fireball lethality to basic missile structures and ceramic materials. Light television towers were used to mount 10-inch solid steel and aluminum spheres, hollow steel cylinders, and aluminum spheres with ceramic inserts. Specimens were also placed in the shot cab. The first tower was only 60 feet from the shot tower, with 4 others erected close behind in a descending pattern. Although it was anticipated that most specimens would be lost, all except those in the cab were recovered. Observations indicate the greatest metal loss was 1.15 inches on the radius of the closest aluminum sphere. Out along the water blast line, several stations had samples of ceramics exposed to evaluate thermal shock resistance. At a remote station on the desert line, a parabolic mirror was set up to concentrate radiant energy on ceramic specimens. Post-shot visual examination revealed severe glazing from the high thermal flux. Cloud growth studies were made throughout the Teapot series. The life history of each atomic cloud was recorded by time-lapse photography from birth to eventual dissipation by winds at altitude. Analysis was made of the influence of weather parameters on cloud evolution. While radiochemical sampling of atomic clouds is now routine procedure, special penetrations were made on Teapot to determine the radiation hazard to flight crews and to evaluate the contact radiation hazard from contaminated aircraft to ground crews. It was found that penetrations as early as 15 minutes after detonation could be made without significant radiation hazard to flight personnel. Surveys of aircraft contaminated from early cloud penetrations established a correlation between standard gamma meter readings and the actual contact radiation hazard, and indicated that maintenance and service work could be performed by ground crews without radiation injury. One of the most important single projects of Teapot was the drone blast study on Met Shot to investigate lethal effects of blast on aircraft structures in flight. 3 drone F-80 jet aircraft were to fly at 3,800, 4,300, and 5,100 feet above the shot tower. For evaluation purposes, it was necessary that the aircraft receive a single-peak ideal type shock wave. It was planned that the drones would receive severe, moderate, and light damage with the possibility that the lower drone would be destroyed. A prerequisite of this test was information as to where the incident and the reflected shock waves would merge over the fireball. Past tests indicated that the reflected shock wave is greatly accelerated as it passes up through the fireball and could merge with the incident wave. This point of merger and the overpressure versus distance after merger had to be accurately predicted in order to position the drones. Therefore, on development shots, Turk and Apple I, blast measurements were made from parachuted canisters and by rocket-laid smoke trails and shock photography. Analysis of these data indicated that the desired test conditions would occur at the altitudes of interest. Operations for the project were based at nearby Indian Springs Air Force Base. Rehearsals with the drones and the control craft were frequent, since split-second timing was essential to success of the mission. For easier identification, the top half of each drone was painted with a bright fluorescent color, while the bottom was painted white to reflect thermal radiation. Each drone was completely instrumented for input and structural response data, which were necessary for empirical correlation with analytical prediction of loading and response parameters. Instrumentation was designed not only to record, but also to telemeter data to stations on the ground. Under the canopy, a set of cameras was installed to record those crucial seconds when the blast hit the aircraft. The instrument panel was photographed as well as each wing and the tail section. Provision was made to eject the entire unit and lower it by parachute should the aircraft become unflyable. Each drone plane was accompanied by 2 mother aircraft, one in control and one as standby, while 2 chase planes tagged along, armed to shoot down the drone in case of malfunction. The decision for detonation of Met was dependent upon the position of the drones, and provision was made for cancellation of the shot at any time up to H-hour minus 30 seconds. As a safety precaution, the direction of flight was planned so that any damaged or destroyed aircraft would crash into the uninhabited area to the northeast of Frenchman Flat. High-speed photography records the path of the drones as they pass through the shock wave above the fireball. The wingtip instrument pods of the bottom drone are blown off and drop in an arc to the ground. The bottom drone, en route to the emergency landing strip after the burst, crashed because of loss of control before landing could be accomplished. The middle drone was landed successfully on the Dry Lake emergency strip, while the top aircraft was brought back to Indian Springs. There, the nose wheel collapsed after landing, and a pileup occurred at the end of the runway. The 3 aircraft had been positioned to receive severe, moderate, and light damage from the shock wave. In general, less damage was sustained than expected. The yield was lower, and thus the blast was lower than expected. Studies of the results will have important application in air defense problems to predict in-flight response for other aircraft types. The most unusual of the Teapot series was the HA shot, planned to be released from a drop plane at 50,000 feet for detonation at an altitude of 40,000 feet. Never before had an atomic bomb been detonated at such a high altitude, nor was it easy to erect a blast line in the sky on which to attach instrumentation. The objective was to determine the magnitude of the basic effects, blast, thermal, and nuclear radiation, in a rarefied atmosphere in order to facilitate progress of the air defense program. These data, along with diagnostic type data, would be of great value in analytical studies and extrapolations of weapons effects to altitudes of 100 to 150,000 feet. The low-altitude device, WASP Prime, was airdropped to burst at 800 feet above terrain, or about 5,000 feet above mean sea level, and the effects and yield were measured. Predictions for the high-altitude burst indicated a slight increase in the lethal radius of thermal radiation, a small decrease in the radius of lethal blast, and a significant increase in that of nuclear radiation. For the HA shot, 8 jet aircraft were to lay smoke trails in horizontal rows 400 feet apart and 2,000 feet above the estimated point of burst. Photography, recording shockwave movement relative to the smoke grid background, would determine free air peak pressures versus distance. Then, the dropped plane would release the weapon, followed by a cluster of smoke grenades, which would be photographed to determine arrival time and particle velocity as a function of time. A string of parachuted canisters would be released next to form an aerial blast line to record effects data and to telemeter pressure information to stations on the ground. Operations base for this project was again the Indian Springs Air Force Base. The instrumentation loaded into the canisters consisted of threshold and fission detectors to measure neutron flux, pressure gauges to measure overpressure, and film badges and dosimeters which were fastened to the inner circumference of the canisters to record total dose of radiation. It was anticipated that the pressure range would extend from 10 psi to 1/2 psi, and radiation from 40,000 rem, or Röntgen equivalent man, down to 25 rem. Some thermal effects instrumentation was also carried by the drop plane. HA was scheduled as a daytime burst. Burst 0 was a point about 6 miles high above Yucca Flat and several miles north of the control point. Some blast and thermal measurements were to be recorded by instrumentation on the ground. Total thermal energy, total irradiance, and spectral distribution versus time were obtained from calorimeters, bolometers, and spectrometers. Camera stations were located at selected ground points to obtain high-resolution photography of smoke trails to determine free air peak pressures versus time and distance, and to determine effects of rarefied atmosphere on shock pressure. It was essential to have an absolutely clear sky with wind speeds at all altitudes below a certain maximum. From the ground, the drop plane was almost invisible to the naked eye. An engine failure resulted in the use of a previously established alternate release altitude of 46,000 feet, giving a burst height of 37,000 feet above sea level. An important factor contributing to the success of this shot was the Air Force capability to make successful cloud penetrations at extremely high altitudes to obtain samples for radiochemical analysis. The radiochemical yield for HA was 3.1 kilotons. Studies of the two shots indicated that there is no significant change in the partition of energy at 37,000 feet. However, a one-to-one comparison of the weapon effects for the two shots, with a significant variable being the change in ambient atmosphere, indicates that the aircraft kill radius for thermal radiation was slightly less on the high-altitude shot, while that of blast was essentially the same. For nuclear radiation, however, the immediately incapacitating and quickly lethal level of 5,000 Röntgens had a radius of 2,350 feet for the low-altitude shot against 4,700 feet for the high-altitude shot, an increase of 100%. The great increase in the lethal volume of nuclear radiation is the most significant effect of a high-altitude detonation as applied to air defense against manned aircraft. A summary of military effects studies during Operation Teapot indicates that while important investigations were made of surface and underground parameters, the greatest emphasis was placed on the potential use of atomic warheads against hostile aircraft and missiles. Vital data were obtained on the effects of nuclear detonation at high altitudes and the lethal effects of blast on aircraft in flight, problems of the utmost concern to the present and future air defense of this country. Operation Teapot now takes its place as a significant contribution to our ever-growing encyclopedia of atomic weapon research.